Right, so I'm going back to section 11.4, the reverse of chain rule. The reason being is because in the first instance we've used substitution. Substitution is foolproof as long as you do use the correct substitution. But there is a little bit of room for, if you try something doesn't work out, you can try something else. Now here is what we're going to do it the way the book designed it to be done. They wanted you to use a quick method. So by recognizing and then adjusting the amounts to find a solution. So perhaps thinking what has been differentiated to give you this answer. So over here, you could see very clearly that this is the example of a function in the denominator and its derivative in the top. Whenever this is the case, and this is exactly the case here, x squared plus 1 differentiates to 2x, you could see straight away that this was ln of the denominator that was differentiated, and the job is done. Okay, you can always check by differentiating. Okay, so you have differentiated, it will go to 1 over x squared plus 1, and then you times it by the derivative, so you have 2x on the top. Okay, now over here again you've got a fraction, so you think, is it ln? Have I got a function on the bottom of the fraction that differentiates to the top of the fraction? And you don't quite have it, because you have got the derivative but half of it. So really you really could do with a 2 cos x here. So if you write it as a half of 2 cos x over 3 plus 2 sine x dx, you could see that this here is an example of a function's derivative over the function, therefore example of ln being differentiated. So it's a half of ln of 3 plus 2 sine x. Actually 3 plus 2 sine x doesn't need modulus because it's always positive, but it's fine if you leave the modulus symbols. Okay, so the second rule is to do with the power function. So if you spot that you've got the derivative of that function that gets a weird power, so you've got the derivative and then a function with a power, then it may have been the chain rule that was used. Okay, so if you think about this one, you've got the derivative, so you don't really want to be looking at this. You've got this function here, sine to the power of 2. So what has been differentiated to give you this result? And your guess should be, if you add 1 to the power, you'll get sine cubed. So sine cubed, if you quickly differentiate it, it will go to 3 sine squared x and times it by cos x. And look at this, you've got exactly that. Therefore, the integral must be sine cubed x. Okay, over here again, you could look at the inside function that differentiates to 2x. Now you haven't got 2x, but you've got a multiple of it, you've got half of it. So that must have been this to the power of 4 that was differentiated. So try differentiating x squared plus 5 to the power of 4. 4 comes down, okay, and then you will have x squared plus 5 to the power of 3, and then you need to multiply it by 2x from differentiating the bracket, so 2x. So you've got 8x x squared plus 5 to the power of 3, but we don't have 8. We've got 1/8 of that answer, so that means x squared plus 5 to the power of 3, let me just write it like that, must have been 1/8 of that function differentiated. Okay, so the answer over here is going to be 1/8 of x squared plus 5 to the power of 4. So let's do 2 last examples using the quick chain rule. So here we've got a function. If it was in the denominator on its own, so not with the power of 3, and its derivative would be in the numerator, then it would be ln. But as soon as the expression in the denominator gets a power of 2 or 3 or other power than 1, then it's going to be the power function. So what has been differentiated? If you think about it, let me just write it on the one horizontal line. 2 plus cot x to the power of minus 3 dx. So if you think about it, what was differentiated? Well, if you add 1 to the power, that will be the power of minus 2. So try differentiating 2 plus cot x to the power of minus 2 and see what you obtain. So you will have minus 2 comes down, and you will have 2 plus cot x. Take away 1 from the power, you get minus 3, followed by cot differentiated. So cot goes to minus cosec squared x. So if you multiply minus 2 by minus 1 here, that will be 2. Let's put cosec squared x at the front, and it's 2 plus cot x to the power of minus 3. So what was differentiated? This function. But we haven't got that many. We've got half of that. So the integral must be worth half of what was differentiated. So it's a half of 2 plus cot x to the power of minus 2 plus c. Okay, and then here, let me just check that I've copied this. It must be tan x here. Or is it tan x? Yeah. Okay, so I'm just going to show the integrating part. I'm not going to do the limits or anything else solving, because we already solved it in the previous video, in previous section. Okay, so over here again, if you think about sec, the problem with this one, what makes it difficult, the fact that sec, the one with the weird power, differentiates to tan, sec tan. So really, let's just write it, 5 sec x tan x. So that represents that derivative. And then you've got sec cubed x dx. So now you need to think, what should I try to differentiate to obtain this result? Well, let's just simply add 1 to the power of sec. So let's try sec to the power of 4x. So that will go to 4 sec to the power of 3x, and then sec x tan x. This will give me 4 sec to the power of 4x tan x. Now, that here integrates to this. Okay, now I don't have 4, I've got 5. So I need to times it by 5 and divide by 4 to get rid of that 4. And obviously I need to do the same to this side. Okay, so my integral over here will be 5. Let's put tan x first. Yeah, must be 5/4 of sec to the power of 4x plus c. And then you carry on and solve this equation. So this takes you to exercise 11D.